Welcome to the training session on Discrete Storms. My name is Dan Bicus. Our learning objective is to provide an introduction to how GOES-R capabilities can be utilized to identify and track discrete thunderstorms. First, we'll take a detailed look at two events with 1-minute imagery from GOES 14 SR-SOR, and then we'll look at a few applications of baseline products to discrete storms. This is a schematic of a supercell with satellite signatures that you may see at times in the visible imagery. We have our familiar anvil cirrus with overshooting top, and downstream from the overshooting top, the above anvil cirrus. The flanking line is typically southwest of the main updraft. The last two features are of primary interest here and indicate that a storm is undergoing intensification or is at or near peak intensity. East of or down shear of the flanking line, you may observe inflow feeder clouds as depicted in this visible image. Much like the enhanced V satellite signature, they are not necessary for severe weather occurrence. There's a number of reasons why you may not observe them, but if you do, think of it as a bonus and keep these numbers in mind. A study found that if inflow feeder clouds are observed, there's a 77% chance of severe weather within 30 minutes, and that number goes up to 85% if coupled with mesocyclone detection from the MDA. West of or up shear of the flanking line, you may observe lines of towering cumulus that form above an invigorated RFD. These clouds do not act as inflow into the storm the way inflow feeder clouds behave. Instead, they develop above the RFD and are an active area of research. What we know at this time is that when you do observe these clouds, the storm is intensifying and or near peak intensity. As proxy data for GOES-R, we analyze 1-minute imagery from GOES 14 SR-SOR, for this case from May of 2014 over Colorado. The most obvious aspect of this loop is the intensification of an isolated storm near Denver that is moving eastward. What specific indications are we looking for other than growth in aerial coverage of anvil cirrus and overshooting tops? Well, the storm has a crisp and distinct edged anvil on the upshear or southwest side of the storm. We observe a flanking line on the southwest flank of the storm, and east of that we notice lines of cumulus moving rapidly towards the storm. In the later portion of the loop, these are associated with inflow feeder clouds that are east of the flanking line. West of the flanking line, we have an invigorated field of cumulus that forms above the RFD. These clouds, as well as the inflow feeder clouds, are indications of an intensifying storm near its mature phase. The invigorated field of cumulus west of the flanking line doesn't last as long as it dissipates about midway through the loop. However, note what we can see once those clouds dissipate. I'll go ahead and circle it. These are not clouds since they're not moving. This is actually a hail swath. This is a picture of the hail swath. It's caused by the storm, which produced a significant depth of hail over a large enough area to be seen in the visible channel due to its higher reflectance. The 1-minute imagery helps make this appear more readily. Let's compare that to the GOES West perspective with its 15-minute temporal resolution. I'll put my cursor on the hail swath. Notice how it's much more subtle than the 1-minute imagery. Now let's look at some satellite signatures of discrete storms from the IR perspective. This is the Himawari 10.4 micron band for discrete storms over Bangladesh. The overshooting tops are indicated and easy to spot as localized minima of brightness temperatures, indicating the storm updraft. The enhanced V signature is inside of this box with relatively warm brightness temperatures existing immediately down shear of the overshooting top, with colder brightness temperatures on either side to form this V shape. The enhanced V signature indicates the storm is most likely severe. However, much like other satellite severe storm signatures we discuss, there are a number of reasons why one may not see the enhanced V signature, so one cannot conclude the storm is not severe in the absence of the enhanced V signature. Here's a composite of GOES 14 SR-SOR 1-minute visible imagery, a time-lapse video taken from Cheyenne, which is located right here, looking at this storm to the northwest, and this is the half-degree reflectivity field. What we're going to do first is look at the time-lapse, and you can see the main updraft base associated with the storm in this vicinity. Over here you can see pulsing updrafts associated with the flanking line on the southwest flank of the storm. And then over in this region you can see an inflow band moving towards the storm. If we focus in on the 1-minute visible imagery, here's the overshooting top associated with the storm, with above Anvil Cirrus moving off in this direction. Here's the flanking line. Remember, there were pulses of updrafts on the southwest flank of the storm that we just looked at. And one of the other things that we see in the imagery are these mid-level clouds that appear and disappear. This is something you probably would not have seen with RSO, and almost definitely would not have seen with 15-minute scans, at least the nature of these clouds. So with 1-minute imagery, you're going to see things like this much more frequently. In this particular case, these appear to be associated with a gravity wave. Notice this line that emanates away from the storm, and you can see it moving towards the south. That's likely the gravity wave. It starts off from the main updraft and emanates out away from the storm. And then think of the ascending branches, or the ascending portion of the gravity wave causing the clouds, and then you'll have these descending regions associated with the gravity wave as well, where you see the clouds go away. Let's go back to our composite, slow down the loop, and we'll go ahead and look at these mid-level clouds in a little bit more detail. First, I'll focus in your attention on the region before they develop, which is here, which starts off relatively clear, and then we see the development of these mid-level clouds in this region. Go ahead and zoom in the imagery. These are the clouds we're looking at right here. So as we were looking at that loop at certain times where we saw those mid-level clouds, portions of those were underneath the anvil, where couldn't quite see those in the visible imagery, and then at other times they're visible over here in the time lapse, and we see those mid-level clouds. One of the things we can say with pretty good faith here is that these mid-level clouds developed in the later portion of the loop. And in the later portion of the loop, you can see that that storm was definitely on a downward trend, a weakening trend. The one thing we can't attribute that to in terms of as a cause and effect, we're not sure if these gravity waves are associated with a weakening of the storm or not. The point I want to make here is that when you have the 1-minute imagery with GOES-R, you're going to see things that you just haven't seen that often in the past, such as this. At times, it's going to make perfect sense to you in terms of what you're looking at. And other times, such as this, it may be an open-ended question, scratching your head, what's going on? Is this associated with a weakening of the storm or not? And that's okay. It means that as you gain experience looking at the 1-minute imagery, and also open up possible research opportunities, you'll begin to understand the 1-minute imagery as time goes along. Let's move on to the next time period.
And we'll start off with the storm we had been talking about near Cheyenne, Wyoming. And you can see that it moved towards the southwest, actually went through a brief reinvigoration, I'll call it, just before it completely went away. And likely what happened with that storm as it moved further to the west did move over some higher terrain to some elevations up around 7,500 feet. And then it moved east again, perhaps moving back into its own outflow and dissipating the storm. Meanwhile, you see additional convection further to the north in Wyoming. But what we're going to really focus in on is what was happening down here in Colorado. We see three areas of active convection. Over the Palmer Divide, we see multiple storms decaying and leaving outflow boundaries for new storms. And by the end of the loop, it looks like the convection has consolidated into one primary updraft that we see in this region with a more pronounced overshooting top. Another area to look at is over the northeastern plains in this general vicinity, which doesn't look as robust as the convection we had just mentioned down here. And then finally, further northwest near Denver, in this region, we see an additional area of convection, perhaps along an outflow from the earlier storms. Keep in mind, still no tornado reports through this time period. And finally, remember the line of cumulus that we had been following here. By the time we get to the end of the loop, we can see it start to get some towering cumulus as it's approaching the front range. In other words, it's moving upwards in elevation here. So we're going to keep an eye on that as we move to the next time period. We move forward to the last time period, and we first focus on the Palmer Divide convection down here. And we can see that this particular storm now looks much more intense with a well-defined overshooting top, an enhanced V that comes out something like so. And the storm has taken more of a turn to the right. Looks like it's moving more to the southeast than it was earlier. On the western flank of the storm, it appears that we have invigorated cumulus above an RFD, which is a sign that the storm is undergoing intensification or near its peak intensity. And then on the southern flank of the storm, we can see this line. Go ahead and draw it in right here. That appears to be intersecting the main updraft here. So we may have this boundary intersecting with this storm. So I'll go ahead and let that loop, and you can clearly see that line moving into the main updraft here, with the western edge of that line bent back to the north into the inflow region of that storm. Multiple tornado reports are associated with this storm, along with very large hail up to baseball size. Meanwhile, north of Denver, the line of cumulus that we had been following, I'm going to stop the loop and highlight that line of cumulus right here along the front range north of Denver, now begins to get some towering cumulus with it. And it just continues to grow. So now storms are developing along this line that we had been following. Meanwhile, remember that convection we had been following further to the south is continuing to slowly move to the north. It looks like at times new storms going up along outflow boundaries from some weakening convection. But we continue to advance along and stop it a little bit later in the loop here. And what happens is actually pretty interesting here. We get looks like a few different updrafts along that region further to the north. And then we have a storm in the vicinity of Boulder down here. That southernmost storm continues moving to the north. It looks like it lays down an outflow boundary. We go to the next image, an outflow boundary just north of that storm, and we get a new tower right here. And then notice that we have on the southern end a pretty vigorous looking storm right here with this overshooting top. Continue to advance along here, and it looks like what happens soon after that is we have an intersection likely between the southern end of the storms that we had been following and the northern end of the outflow of the other storms that had been coming up from the north. And right where those intersected, we get really enhanced overshooting tops here by the end of this loop. And in that particular area, there was a tornado reported along with egg-sized hail. So a number of interesting things that you can see here in the 1-minute imagery, and information that you can make use of not only in terms of how the near-storm environment is evolving here, but also during the warning decision-making process, how these various boundaries are interacting. You can quite rapidly see how these new overshooting tops go up. And remember, when GOES-R comes along, we get that 1-minute imagery, you're going to have this imagery on your AWIPS in about 1 minute, which will enable you to actually use it during the warning decision-making time period.
Cloud top cooling trends to assess storm intensity can be obtained from the IR band at 10.4 microns. The tracking meteogram tool in AWIPS can be used to display cloud top cooling trends. In this example from Himawari over Southeast Asia, we place the AWIPS cursor for the tracking meteogram tool over a discrete storm that develops. The plot of brightness temperatures with time is plotted on the right. As you gain experience in using this tool, you will gain a better understanding for what cloud top cooling rates are significant for your CWA. We now switch gears to highlight some applications of baseline products to discrete storms. We begin with 1-minute visible imagery coupled with lightning. At the 2016 spring experiment at the Hazardous Weather Testbed, forecasters analyzed proxy GOES-R data for real-time events. This included 1-minute visible imagery from the GOES-14 SRSOR and lightning data from an LMA for an event over northern Alabama as proxy for the GLM. The forecaster was analyzing a line of storms that looked pretty much equal until there was an overshooting top in the 1-minute imagery, along with an associated lightning jump in the flash rate data. The forecaster warned on the storm based off this information, and quarter-size hail was observed. This example illustrates the value of blended baseline products with 1-minute imagery to improve warning effectiveness. The next baseline product we'll discuss are the derived motion winds. These winds are derived from cloud motions from satellite imagery and will be useful in the GOES-R era with its higher spatial and temporal resolution. The winds are calculated based on the level and the vertical of the cloud, so that a variety of cloud heights will provide winds at a variety of vertical levels, which can provide useful information on the vertical shear profile. You may also be able to identify regions of localized low-level convergence and associated boundaries for convective initiation or intersections with existing storms. You may also use the winds to validate familiar model analyses or forecast. Other applications of derived motion winds include assessment of storm motion, upper-level diffluence, and as depicted in this loop, you can detect developing and intersecting boundaries in the winds. Therefore, this data source provides a more rapid update compared to familiar hourly model analyses. Time for an interactive exercise. For this exercise, I want you to match the following satellite severe storm signature to the correct image. Either lines of towering cumulus above an invigorated RFD or inflow feeder clouds. So I'll give you some time to think about this, and we'll look at the answer on the next slide. Here's the answer to the interactive exercise. This image shows lines of towering cumulus above an invigorated RFD on the western flank of this storm. And over here, we have inflow feeder clouds on the southern flank of this storm. In summary, the 1-minute imagery will have numerous applications for identifying and tracking discrete storms. The increased spatial and additional bands available with GOES-R will also be helpful for discrete storms. GOES-R baseline products will have multiple applications to discrete storms as well.